Okay, so this is our project for Mechanical Design 2. Our group consists of Newman, Jonathan Groot, and myself, Scott Lyon. This is for EML 4501, fall of 2016, and this is welding technologies and thermite rail welding concept that we came up with. So the project description, we were tasked with reviewing contemporary problems related to engineering technologies. Based on this research of the history, the current designs, and the future developments, we wanted to come up with a concept to improve upon existing practices. Okay, so welding is the process of joining two materials, typically by the process of fusion. It does differ than brazing and soldering because those do not melt the base metal. In order to create a stronger weld, the use of pressure heat can also be used, either individually or combined. And as I said, basically the main point of welding is to melt the base metal, and you can also add filler materials to increase the strength. Some of the most common types of welding in the world today are electric welding, also known commonly as stick welding, TIG welding, or gas tungsten, MIG welding, which is gas metal arc, flux core, submerged, and electroslag. The process is very attainable to many people. It can be performed and implemented in many situations and environments. It can be performed underwater, in the air, or even in space, working on ISS or satellites. It definitely plays a tremendous role in our modern world as well as our history. And as I said before, it has a very broad industrial and private application. And this is mostly due to the energy sources. Energy can come from something as simple as gas flame, UV radiation, or an electron beam. Okay, so this picture on the right shows one of the first fully welded iron structures in the world. It happened in 310 AD. It's known as the Iron Pillar of Delhi. It weighs 5.4 tons. Basically developed in the same time, was one of the most common forms of welding that we all know, which is forge welding, which is where you see blacksmiths working on weapons, armor, horseshoes, anything during that time. So through the Middle Ages, forge welding continued to advance, primarily due to the heavy demand of blacksmiths and how skilled they've become. The metal is heated and then pounded repeatedly until the bonding occurs or a certain shape or physical trait is acquired. Quenching can also be used to add strength, which is when they dip it into either water or chemical after the forge. Forge welding was really one of the only existing technologies that was heavily used until the 1800s. In 1800, Sir Humphrey Davy discovered the short pulsed electrical arc. Simultaneously, because they didn't know they were working on at the same time, Vasilij Petrov discovered the continuous electric arc, which was a little bit more stable, but again, they didn't know that they were both working on the same technology, and they're both credited with the discovery. Okay, so this is just a historical perspective. 1885, we had resistance welding. 1930, massive expansion of arc welding, which is what a lot of use today, and this is basically due to World War II, and I, I guess, for that matter. And something as new as 1958, plasma arc, electroslag, and electrogas.
My name is Newman, and I'll be talking about current welding methods. So this is just a list of some of the current welding methods we'll be talking about, but given the time limitation, I won't be able to go into detail on each one. I'll just do a quick overview and try and convey the concept and idea to you. So to begin, we'll start with oxy-fueled gas welding. So basically here, heat is produced by the combustion of acetylene, and here's the diagram that shows the welding torch, the material to be welded, and also the filler rod. Sometimes filler rod is coated with a flux material, and what that does, it actually creates, which is not shown in the diagram, shielding gas to protect it from contaminants in the air and such. The next one is arc welding. With arc welding, you now have an AC or DC power supply and an electrode which you are actually using to weld. With the electrode, you can have both consumable and non-consumable electrodes, and as the name implies, with consumable electrode, the electrode begins to get shorter and shorter every time, and that's because when it consumes the electrode, there's actually a shielding gas, which, again, as I said before, creates almost like a protective barrier against contaminants, and it's actually not shown here. And with arc welding, temperatures may reach up to as much as 10 times greater than in oxy-fueled gas welding. The next method is ultrasonic welding. Here, materials are subjected to a static normal force along with oscillating shearing stresses. And here's the diagram where you have the two materials to be welded. You have a force acting in the vertical direction and the shearing stresses acting in the horizontal direction. And here's where the weld will be created. And this method is usually used for plastics. The next is friction welding and friction stir welding. So here, the heat necessary for a weld to be made is brought on by friction. In the picture to the left, you can actually see like what you could say a friction spot weld, where one of these members actually rotates really fast and is pushed against the other member, and that's what creates the weld. In the picture to the right, you see what's called friction stir welding. The concept and idea is the same, where the heat's created by friction. It's now just moving along a direction and along a seam. And basically you can see the probes stirring the material to the bottom right of the diagram there. The next is resistance welding. So the weld is created by the electric resistance between the two materials. Here in the diagram you can see both electrodes, metal A and metal B, and the highest point of heat is actually at the where the two metals contact each other, and then that's where the weld nugget is and where the weld will be created. Also, you have resistance seam welding. Concept again remains the same, except you're now creating a seam, and the electrodes are basically the two wheels that the seam would pass through, the two materials would pass through. Next, we've got electron beam welding. Here you're using electron beams that are accelerated towards the workpiece. When the electrons actually hit the workpiece in the vacuum chamber shown in the diagram, that kinetic energy of the electrons is actually transformed into thermal energy, which creates the necessary heat to form the weld. Next is laser beam welding, and as you can imagine, a laser beam is actually shot towards the workpiece and where the intended weld is to be. And here you have a powder nozzle, and instead of powder is used, and you could say it's the equivalent of a filler rod as you'd use in oxy-fuel gas welding. And here you can see the weld lead actually creating. So the heat in this method comes from the laser beam. And finally, we have exothermic and thermite welding. This is a welding method most popularly used to weld railways, as you can see in the picture to the right. And here the heat necessary to form the weld is actually generated by the combustion of a thermite material. And here's a diagram that actually shows it, where you have the material being fed through and then the combustion chamber there where the weld would be created. And finally, now if we actually look to the future developments of welds, since the 1970s, no new methods have been developed, and instead the focus has been shifted on weld efficiency and weld accuracy as well as quality. We can expect to see a huge growth in automated welding, and as such we can see a decrease in skilled weld workers. Also, you can say, or it can be implied that with engineering, now more designs will be more efficient and that they'll require less welds, and so we'll see almost a decrease in welding.
Hi, I'm Jonathan Groot, and for our design we decided to focus more on thermite welding for the railroad application. This being because, like Elijah said, there have been no new technologies in welding over the last few years, so we decided to focus on an existing one, more primitive one actually, but see if we can get it more modernized and automated. Essentially, what this thermite welding is just done to join two rails together in the construction of the railroad industry, and it's still today, even though trains are a thing of the past technically, you still have bullet trains and as a means of transportation, it's still a very relevant technique. So basically our design was simple. We decided to take the different features of thermite welding and combine it into one fully automated machine that will have an aligner in front that aligns the rails, the actual thermite welding plant which welds them together, and then a grinding module which comes after and grinds off the excess welding around the rail so that the train can travel smoothly on it. So this is a basic schematic of the thermite plant. Basically it's made up of a mold at the bottom and the thermite cylinder on top. So thermite welding is basically, you have a powder of iron oxide and aluminum, and it's mixed with an igniter, and after that is lit, it burns, it undergoes an exothermic reaction, and it results in molten aluminum oxide and molten iron. The molten iron is a lot more dense than the aluminum oxide, and as a result, it settles to the bottom first, fills the gap in the mold, creates the weld, and the molten aluminum oxide is then overflowed and gotten rid of. It's then left to cool over time so that the weld is strong, and then eventually the mold is removed What's left is the gap is welded together, and there's also iron welded around the outside, which then needs to be removed. So we decided that the automated system is simply going to have 3 grinding wheels. The one on top will be contoured to the shape of the top of the welding rail, just the top there with the corners, and then you're going to have 2 more grinding wheels off to the side that's going to smooth the sides off, so that when the wheel of the trail sits on it, because it sits on top and the side of the rail, it can travel smoothly. Also, we decided to do it with some tolerances, because a lot of times the rail, when it's manufactured, isn't exactly smooth and it has some roughness to it, so we left tolerances for that. Also, we hope to make this sustainable in that it has a solar panel on top to power it, so that you can essentially load it up with the different Thermite cylinders, send it off, it goes down the rail, and it does its job all by itself. Alright, so while doing this project, we gained a broader knowledge on welding technologies and the methods. We gained a good insight into the history and how far it's come. And because of the vast improvement in it during the turn of the 19th century, it has somewhat slowed down, so we decided to focus on advancing one of the existing technologies. And we used this new insight, obviously, to improve upon an existing method. And as a result, we came up with our design, which we hope to improve and get it, as something that's manufactured and sold out there.